second equation is P1 plus P2 equals 35 minus Q2. That part, Jacob is right. What we want to solve for P1 and P2 as functions of Q1 and Q2. So what do we do? Well, you just treat this as two linear equations. On the right-hand side, you have 40 minus Q1 here, 35 minus Q2 here. And how would you solve for P1 and P2? What's the easiest way of solving? What was the method I taught you a week ago? Okay, or using what rule? Cramer's rule. Just use Cramer's rule. So, just use Cramer's rule. Solve for P1. It would be as follows. P1 equals the ratio of these two determinants. So the determinant of the coefficient matrix is just this. 2, 1, 1, 1. And up here, for that first column, you substitute in 40 minus Q1. See, this is just like a number. Before it was a number. But it's just an entity. 40 minus Q1, you substitute that in. You substitute in the 35 minus Q2 here. I'll just put parentheses around these if you like. And then the rest is just 1, 1. So you just use Cramer's rule. And treat these things on the right-hand side as the right-hand side constants. So that's all we're doing. So here we get to 2 minus 1 is just 1. Here you get 40 minus Q1, because you multiply that times 1, minus 35 minus Q2. And this just reduces to 5. 40 minus 35 is 5. Minus Q1 plus Q2 over 1. So you just leave it like that. So that's your P1. And then you solve for P2 using the similar method. Okay. So P2 would just be this. The determinant in the numerator is just going to be, let's see, what was it? The first was 2, 1, and then you substitute in here. So this will just be 2 times 35 minus Q2 minus 40 minus Q1. Or it will be 70 minus 2Q2 minus 40 plus Q1. So this will be P2 equals 30 plus Q1 minus 2Q2. Okay, so that was really the trickiest thing about this problem. Now you've gotten rid of P1 and P2, so you can go back to this and substitute in and get your profit function. So it's this. So let's substitute in for P1. What was it? 5 minus Q1 plus Q2 times Q1 plus P2, which is 30 plus Q1 minus Q2 minus 2Q2, right? times Q2. Okay, so I have that right? Yeah, okay. Then you have a minus Q1 squared minus 2Q2 squared minus 10. Okay. Now we can multiply this out, and what do we get? It's a little bit messy, but 5Q1 minus Q1 squared plus Q1 Q2 plus 30Q2 plus Q1 Q2 minus 2Q2 squared. Minus Q1 squared minus 2Q2 squared minus 10. And then that simplifies just a little bit, doesn't it, to this. We can simplify this profit function, which is now expressed as a function of Q1 and Q2. And it's what? 5Q1. Let's see, we have a minus Q1 squared here. We have another one here, so it's minus 2Q1 squared. We have a Q1, Q2, and another Q1, Q2. So it's plus 2 Q1, Q2. And then what else do we have? We have a minus 2Q squared minus 2, so it would be minus 4 Q2 squared. And then we have our minus 10. Okay, so it's simplified rather dramatically, did it? Okay. That's really the hardest part of the problem. Oh, did I? Oops, excuse me. I left off that, didn't I? Thank you, Brianna. Did I leave off anything else? Thank you. We need this term right here. Thank you. So, thank you, thank you. Okay. Then we have our minus 4Q2. Simplified it a little bit too much, didn't I? Minus 10. There we go. Okay, I think that's complete now. But we definitely needed that 30Q2. Okay, that's your objective function that we want to maximize. So what are the procedures we follow for finding the maximum? You haven't forgotten. It's been only a week. Okay. Okay. Take the, what kind of derivatives are they? Partial derivatives. And there's going to be two of them. So take the partial derivative of profit with respect to Q1. And we will just call this, Will, pi 1. And Will, what is pi 1? Okay. Okay, yeah. At this point, let's just go ahead and write it out. 5, you're right. Plus 2. Yes. We're differentiating with respect to Q1. So right here, the coefficient on Q1 is really 2Q2. Right. And what do we do with that derivative now that we have it? Set it equal to 0. Right. This gives us a linear equation in Q1 and Q2. But we need to look at our other partial derivative too. Pi sub 2, which will be equal to what, 30 plus 2q1 minus 8q2. Okay. So you have two linear equations and two unknowns you can use for Cramer's rule and get your critical values for q1 and q2. I'll let you do that. Solve for these critical values. Then, and I'll just assert, q1 and q2 both turn out to be positive numbers. In this case, they're fractions. This is a book I took from the book. So the answers are not whole numbers. If I were doing it, I probably would have made the solutions whole numbers. Okay. But then what would the second order conditions be? So let's suppose you've solved for q1 and q2. Do you have a maximum profit there or not? Then what would the second order conditions for a maximum be? The sufficient conditions.
That pi 1, 1.
Right.
And pi 2, 2 are both negative.
Right. Exactly. That would be our sufficient condition. And let's go ahead and work that out. Jacob, what is pi 1, 1?
-4.
Right. And look, something very important here. It's always -4. It's a constant function. Now, if this had involved q1 and q2, we would have had to plug in the critical values of q1 and q2 and evaluate the second derivative there. In this case, we don't, because it's always -4 for all values of q1 and q2. What about pi 2, 2? All right. So this is always negative. This is always negative. What about pi 1, 2? Pi 1, 2 would be what? 2. Okay. So pi 1, 2 squared is 4. But if you take, as you said, Jacob, pi 1, 1 times pi 2, 2, that is equal to 32. And that is greater than pi 1, 2 squared, which is 16. Oh, excuse me, it's 4. 32 is greater than 4. So therefore, we've satisfied the sufficient conditions. Pi 1, 1 is negative. Pi 2, 2 is negative. Furthermore, pi 1, 1 times pi 2, 2 is greater than pi 1, 2 squared. Now, normally, what you have to do is evaluate these second order conditions at the critical values of q1 and q2. But in this particular case, all these derivatives, second order derivatives, are constants. So what this means, what is the second order total differential? It's not in this case, notice that our dependent variable is pi. It's not z, as it was in the theorem. So, but what is the second order total differential? Well, it will just be this expression here. It'll be pi 1, 1 times dq1 squared plus 2 pi 1, 2 times dq1 dq2 plus pi 2, 2 times dq2 squared. Now, in this case, our second order total differential, if we just substitute in, pi 1, 1 is -4, wasn't it? And this is 2 times 1, or just dq1, dq2. It's pi 1, 2. Pi 1, 2 is 2. Okay, so this should be 4. Excuse me. Plus pi 2, 2, which was equal to -8. Now this second order total differential is negative everywhere. Okay, so this is a negative definite second order total differential. So that means by 1125 that this is what kind of function?
We're at a bowl, upside down bowl.
Right, and furthermore, this function is what kind of a function? Not only that, you got the graph right, but what kind of function is it? It's a strictly concave function, because the second order total differential is negative definite everywhere. Therefore, it's a strictly concave function. And therefore, if you satisfy the first order conditions, as you did at these points, the two values of Q1 and Q2 that satisfy those first order conditions, you have a global maximum. Not just a local maximum, but you have a global maximum. Okay, so this is the primary reason why we study concavity in economics. Because if you know your objective function that you're trying to maximize, you know that that's strictly concave, you satisfy the first order conditions, you're guaranteed to have a global maximum at that point. Not just a local maximum, but a global maximum. Okay. So a lot of times when economists are doing theoretical work, they won't use a specific functional form. They'll just assume, okay, suppose we have a concave objective function. Then they just look at the first order conditions and then they know that you have to have a global maximum there. Okay. So basically what you're doing is you're doing the same thing. You're checking these second order conditions. Only now these second order conditions that you derived before have to hold everywhere at all points on the function, not just at the critical values of, say, Q1 and Q2, but everywhere. Okay. Now, this will be easy to do as long as these second derivatives are constants, but they won't always be constants. Sometimes the second derivatives will be functions of Q1 and Q2. So then it might be a little more difficult to show that your function is concave. And maybe it isn't concave. It's not always concave. Okay. Okay. We still have a little bit of time, don't we? We go from 2 to, what do we go to? 2 to, now come on, this is, all right, here, I have another problem for you to do. This will be an easy one. Try this problem right here. We consider this problem right here. Suppose you have a two-product firm. But both products are sold in competitive markets. Product 1 is sold for this price, P1 sub 0. And I'm not going to specify what the price is. I'm just going to call it P1 sub 0. Product 2 is sold for this price, P2 sub 0. And the firm can sell as much as they want at those prices for product 1, product 2. And the firm's cost function is this. C equals 2 Q1 squared plus Q1, Q2 plus 2Q2 squared. Find the firm's objective function and see if it's concave or not. And develop, find the optimal values of Q1 and Q2. Okay. So how would you begin? Okay, set up the profit function, Will. So can you help us, Will? Okay. Revenue minus cost, that's a good start. Right. Or in this case, we'll call it P1 0. Do they put on the 0, Will? Just to indicate that price is exogenous.
All right.
Okay. Plus.
P2, 0.
Right.
Q2.
Right.
Minus the function.
Right. Yeah, that's simple, isn't it?
2Q1
Right.
plus Q1, Q2.
Exactly.
Q2 squared.
Right. So this really isn't going to simplify anymore. Let me just write it out. I don't think it simplifies much, does it? It's already pretty simple. All right, you got that, Will. Now, how would you determine whether what would be the easiest way of trying to determine whether or not this function is strictly concave or not?
I'm not sure, actually.
Okay.
Second order total differential.
Okay. And the second order total differential, since this is a function of Q1, Q2, the second order total differential is always just this. So what do we need next? What would help us in making progress? Yep. Let's get pi 1, 1, pi 1, 2, pi 2, 2. Okay. What is, actually, let's get pi 1 first, because that will be part of the optimization problem, is to take those first order partial derivatives, set them equal to 0. So what is pi 1, pi sub 1 going to be? Right. 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 Let's say this was, we're doing pi 1, this was Q1. Right, right, right.